All right, the first of our tricky integration methods is integration by u-substitution, which is really doing the chain rule backwards. So we're unchain ruling now. Um, a quick review of the chain rule. Remember, if you do the derivative of something like this, you leave the inside alone, bring down the 4, leave the inside to the 3, then you multiply by the derivative of the inside, right? The inside's left alone the first time, and then voila, there's the derivative. Same thing, tangent of ln x. Ln x is the inside, so we leave that alone. We did the derivative of tangent, which is secant squared. And then the derivative of ln x goes on the outside. So there's the chain rule. Now, if we're going to do the chain rule backwards, that means we're starting with something that looks like this. We have to work backwards and figure out what the original function is. And the trick with the chain rule is you want to identify some inside, and I use inside loosely there because sometimes it's not really inside. You'll see what I mean. Okay, that was stupid. I shouldn't have said that. I take it back. All right. Um, so we're looking for an inside and its derivative somewhere inside your integral, or the integrand, if you want to be technical. And so here's an example. I'm looking at number 1 right here. Um, the inside on this one is easy to see because it's set off by parentheses. So I'm looking and I see x squared plus 7. And then I think to myself, what is the derivative of x squared plus 7? Well, the derivative of x squared plus 7 is 2x. So I see an inside and the derivative of the inside somewhere else. That's a cue that you're going to use u-substitution. Now, the reason it's called u-substitution is because what we'll do is we're going to say, let's let u equal x squared plus 7. And I'm going to substitute u in for x squared plus 7. But when I do that, that changes my variable to a u. And so the next thing I have to do is figure out how to take care of dx and this other x. Oh, let's pause this for a sec. Okay, so I'll let u equal x squared plus 7. Now I take the derivative of u with respect to x, and the derivative of u is going to be 2x. And then one last final step, I can treat du dx like any other fraction. I'm going to multiply both sides of the equation by dx. These cancel. And then that means that du is actually equal to 2x dx. All right. Now the importance of that is once you start to substitute and change your variable, you have to get rid of every single x, including the dx. So in this substitution, the easy one to see is I no longer have x squared plus 7 to the 6. I'm taking that out, and I'm going to plug u in its place. Now, for the rest of the x's, I have to get rid of those, but 2x dx is du. So those two come out, 2x dx, and that is du. So in my substitution, what I've done is I've created a much cleaner integral. I'm just going to change the way that's written. I'm going to get rid of the parentheses. That's the integral u to the 6 du. And now it's a very easy antiderivative. We started with something ugly, and through u-substitution, finding the u and the du, we now have something clean. I can do that antiderivative. I'm going to add 1, u to the 7th, divide by the new exponent, plus c. And so there I did the antiderivative. But then the final step is you need to take your u, which was x squared plus 7, and you substitute it back in the end. If you start with x's, you need to finish with x's. So I'm going to change that to x squared plus 7 all to the 7th over 7 plus some constant. There is your answer using u-substitution. So you identify an inside, you look for its derivative, and then you do substitution based on that u and the du. Let's try this one. Looking for an inside and its derivative. When you have a trig function, a good place to look for the inside is the angle. So I'm looking right here, and I'm going to see what happens if I let u equal x cubed. Well, if I do u, I've got to find du, and the derivative of x cubed is 3x squared. And I'm going to go ahead and skip the step where I wrote du dx and then multiplied by dx, I'm just going to go ahead and stick the dx over there with the 3x squared. So now I have u equals x cubed. Du is 3x squared dx. And it's vitally important. You absolutely have to find your du. 3x squared dx is my du, and I see my du. I see a 3x squared, and I see a dx. So if you can find your du, that means we can continue with u substitution. So now I'm going to substitute all of that out. It's cosine of x cubed, but instead of x cubed is my u, and then 3x squared dx, that's the du. So now I only have the antiderivative of cosine u, which is sine of u plus c, and then you plug your x cubed back in. So our answer is sine x cubed plus c. Here we go. Good, good? Good, good? Hey, I don't know how many more I have. I think I have 3 more. I don't know. Okay, let's try this one. Secant squared x tangent over tangent x dx. And this one's very intimidating because you have a fraction and you have trig, and you hate both of those, but get over it. Now remember, you're always looking for a function and its derivative, and hopefully in the back of your mind, you remember that the derivative of tangent x is secant squared x. And so I see a secant squared and I see a tangent. Since secant squared is the derivative, I'm going to see what happens if I let u equal tangent x. Let's see what this turns into if I let u equal tangent x. Well, I need to do the derivative of that. The derivative of tangent is secant squared dx. And then I'll look to see if I see all of those pieces. And I do. I see u. It's in the denominator, but that's okay. Earlier I said I used the term inside loosely. I put it in quotes a long time ago. It was like a whopping 3 minutes ago. But in this case, the inside is the denominator. There's not parentheses setting off the tangent x, but the inside is, or the denominator is like the inside here. And then secant squared x dx, I need to see that for my du, and I do see secant squared x dx right there. So this turns into the antiderivative of tangent x comes out, that's my u, and then secant squared x dx is my du. And since I took everything out of the numerator, I'm going to hold that place with a 1. And hopefully that looks familiar. 1 over u, 1 over u. That is the derivative of the natural log, except remember we put it in absolute values. And then I just need to substitute my tangent x back in. So this is going to be the natural log tangent x. How does that make you feel? There we go. Good, bad, ugly? Yes, 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 yes. All right, let's try this one. X times the square root of all that stuff. Uh, Now, unless I recognize this derivative, like that doesn't look familiar to me, I'm going to change this function to x, and instead of the square root, I'm just going to change it to 1 plus x squared to the 1/2. The time that I do not change that is if I had something like the antiderivative of 1 over root 1 minus x squared. And I wouldn't change that because I recognize that as the derivative of inverse sine x. So if you recognize it with the square root, then don't bother changing. But number 4 here, I don't recognize. Now, I don't know how to do this derivative. It's not power rule or anything simple like that. So my first approach is going to be u substitution. And always look inside my integrand or inside parentheses for a u. So I'm going to see what happens. Hey, what happens if I let u equal 1 plus x squared? Well, I need to find the derivative of that. And when you find your du, when you find the derivative, you completely ignore the rest of the problem. Don't look at the rest of the problem when you're trying to decide what du is. So if u is 1 plus x squared, Well, what's the derivative of 1 plus x squared? Well, derivative of 1 is 0, x squared is 2x. We'll tack on the dx. And so that is my du. Now, once I find the du, now that I have found du, I go back and I look at the rest of the problem, and I try to find du in the problem. Well, I'm really close. I'm really close. My whole du is 2x dx. What I've got here is an x dx. I'm missing the 2. And so now we have to figure out how can I fix that. Well, if you're missing the 2, if all you're missing is a 2, or any number, if you're just missing a constant, you can fix that. Time to pause. All right, so if all you're missing is a constant, we can fix that, and I'm going to fix that by simply putting, geez, seriously? Okay, so I'm going to put this 2 right there. Hey, look at there. Now I have 2x dx. Problem solved. Woohoo! Um, except we just changed the problem. You can't just change the problem to fit your needs. If we could do that, we just erase it all and change the problem to 3 plus 5 and be done with it. Uh, so since I altered the problem, I have to offset that. And what I'm going to do, since I multiplied by 2, I'm going to multiply by 1/2 on the outside of the integral. So now that 1/2 is canceling the 2 I just put in there. So if you ever need to throw in a constant to fix your du problem, see now I have my du, I have to offset that constant. Now the 1/2 on the outside isn't going to go anywhere. Now when I do my substitution, I have 1/2 times the antiderivative, 2x dx, all of this right here, all of that is my du. All of that comes out to be du. And then the inside, where I have 1 plus x squared, that's my u. So now I have u to the 1/2 du, and the 1/2 on the outside that I had to put to offset my 2 stays there. Well, now I do the antiderivative. The 1/2 on the outside comes along for the ride. I will add 1. That'd be u. 1/2 plus 1 is 3/2. I'll divide by 3/2, which is the same as multiplying by 2/3. Then I will add my c. Then final step, we plug our 1 plus x squared back in. So 1/2 to 1 plus x squared to the 3/2 all over 3 plus c. That will simplify a little bit. You could cancel those 2's if you wanted, but no real need to. Good, good? Good, good. Okay, so that's u substitution. Identify an inside, look for its derivative, and sometimes you have to kind of change it. If you're missing a constant, you have to change it to fix that. If you're missing a variable, then you're out of luck. You can't use u substitution. I think I have one more problem. I think this is the last one. We'll see. Let's see. I have x cubed e to the x to the fourth. And again, y'all don't like this. For some reason, you don't like e. I've never quite figured that out, but you don't like e's. And this is another time where the inside is not painfully obvious. On 4, I think the inside is obvious. There's you're inside the square root. That's pretty easy to see the inside. This one, not so much. But when you have exponential functions, my inside, I'm going to look in the exponent. That's where I want to look. I see an x to the fourth, and so I'm going to see what happens if I let u equal x to the fourth. Okay, so now u is x to the fourth. I'm going to ignore the rest of the problem, and then I'm going to do the derivative of x to the fourth. Let's see, the derivative of x to the fourth, du would be 4x cubed dx. And now we look back at the rest of the problem and see if that's in there somewhere. Let's see, we're close. We're close again. I see my x cubed and I see my dx. All I'm missing is the 4. But if all you're missing is a constant, you can fix that. I'll put a 4 in there. I'm going to offset it with a 1/4. And now I can do u substitution. Let's see, the 1/4 on the outside stays there. Antiderivative. 4x cubed dx. All of that comes out to be my du. And then I have e. I'm not changing the e part, but the exponent on e is my u. So it's e to the u, du, and that's the easiest antiderivative. That'd be 1/4 on the outside. And then the antiderivative of e to the u is e to the u plus some constant. And then finally, we will plug our x to the fourth back in for u. There's your answer. Good, good. I think that's the last one. It is. All right, so there are 5 u substitution problems, and this is where this unit is going to start getting a little bit more difficult because now the antiderivatives are not as straightforward. They're not just recognition. They're not just power rule. You have to do a little bit of analyzing to be able to pick out your inside and your du and all that mess. So there we go. Thanks.